Hi, today I'm exploring this question: how does helium ion irradiation create fluorescent nanodiamonds for bioimaging? This topic is based on a paper by Chang, which was published in Nature Nanotechnology in 2008. Fluorescent nanodiamonds are powerful tools in bioimaging because they are bright, stable, and non-toxic. But until recently, producing these fluorescent nanodiamonds was quite of a challenge because it was difficult and inefficient. This paper shows how helium ions have changed that. So let's start with the challenge. We know that to make nanodiamonds, we need to create NV centers. And this is nothing but when a nitrogen atom sits next to a missing carbon atom. And this whole pair emits red fluorescence. Previously, to create these vacancies, researchers used high energy beams like 2 mega electron volt electrons or 3 mega electron volt protons. But these setups were expensive, inefficient, and produce very few usable FNDs. So it was not scalable. Chang's team introduced a new solution, 40K electron volt. The solution was a 40K electron volt helium ion irradiation. And here's how it works. First, they began with a synthetic nanodiamond that naturally contains nitrogen atom. It already contains nitrogen atoms. So what they wanted to do was to create these vacancies so that the NV centers would be created. In order to do that, they bombarded them with helium ions. These helium cations were able to knock the carbon atoms out and create NV centers. After the irradiation happened, annealing took place. And annealing is nothing than just heating the diamond up to 100 degrees. During this step, vacancies migrate, they move. And they can pair up with nitrogen. So finally, we will have NV centers. And as we said before, these NV centers are what give nanodiamonds their bright, stable red glow. So why helium instead of electrons or protons? There are three main reasons. First, helium ions are incredibly efficient. Just 1 kilo electron volt helium cation ion creates about 40 vacancies. compared to just 0.1 from a 2 mega electron volt electrons. That's 400 times more effective. These are electrons, and these were the heliums. Second main reason is that we all know helium is inert, so it doesn't chemically react with the diamond. It doesn't alter it physically or chemically. And the third reason is that helium ion sources are affordable and accessible. So it means that they can be installed in standard material science labs, unlike the massive particle accelerators. So these three reasons altogether make helium ion irradiation much more practical for nanodiamond production. So what are the properties of these helium irradiated FNDs? They're bright because they emit red light. They're photostable. They don't bleach over time. They're non-blinking, unlike what we see in the quantum dots. They're non-toxic, so they're perfect for biomedical applications and they're safe to use inside the living cells. Their sizes range from 25 to 140 nanometers, so they're small enough for cellular uptake. This matters a lot in bioimaging applications. To have these fluorescence tools. They solve the problems of long-term live cell imaging, these properties actually matter a lot in bioimaging because the traditional nanodiamonds, they bleached quickly. And we all know that quantum dots blink or can be toxic. But FNDs solve these problems because fluorescent nanodiamonds are ideal for long-term live cell imaging, tracking of particles, or targeted drug delivery and monitoring them. And now, thanks to these helium ion irradiation, they're no longer rare or expensive, so we can make them in large quantities, making advanced bioimaging more accessible. So to wrap them up, I can say helium ion radiation creates the fluorescent nanodiamonds by efficiently introducing vacancies into the diamond lattice. It's fast, efficient, and scalable, and the resulting fluorescent nanodiamonds are perfect for high-resolution long-term bioimaging. It's a brilliant example of how material science can directly impact biology and medicine. Thank you for watching.